I'll be covering complex numbers. I would like to start off first by defining a real number. Then we're going to move on to imaginary numbers. Then we're going to talk about operations involving imaginary numbers, powers of I, the complex numbers, and the algebra of complex numbers. All right, so let's get started. So, real numbers. Now, a real number is defined as a number x such that x squared is greater than or equal to 0. Now, what does that mean? It's basically any number that you can think of, right? Any negative, positive, any fraction, decimal, any rational, irrational, any number that you can think of is a real number, right? Inclusive of 0. Now, imaginary numbers, that's defined as a number x such that x squared is less than 0. It's basically a type of number that when you square it, it gives a negative result. I know all your life you've been told that once you square a number, the result is always going to be positive. But that's because you were only operating in the real number system. Imaginary numbers, they tend to break that rule. So if x squared is equal to -4, then x will be an imaginary number, right? All right, so I just deleted that so I can start over the process. Now, let's see what's happening here. Let's see how x is an imaginary number. I said that x squared is equal to -4. If I square root both sides, I'm going to have x is equal to the square root of -4. Now I can factorize -4 into 4, the product of 4 and -1. Right? And using my laws of indices, this will give me the root of 4 multiplied by the root of -1. And the root of 4 can be either positive or -2. And the square root of -1 is denoted as I. Right? So x is an imaginary number. 2i is either -2i or positive 2i. Right? All right. Now we basically use the I to represent the square root of -1. Right? And I is the basic unit of imaginary numbers. So any imaginary number is going to have that unit I in it. Let's talk about algebra of imaginary numbers. Now, the algebra of imaginary numbers is just like the regular algebra that you've been doing all your life. Nothing really has changed besides knowing the fact that I is equal to the square root of -1. So whenever you have to square anything, just bear that in mind. We're going to talk about that. That's the powers of I. But let z1 be an imaginary number 4i and let z2 be another imaginary number -7i. Now with addition, z1 plus z2, that's 4i plus -7i, which is basically 4i minus 7i. And 4i minus 7i is going to leave me with -3i. Right? z1 minus z2 is 4i minus -7i. And 4i minus -7i is the same as 4i plus 7i. That's going to be 11i. Multiplication, 4i multiplied by -7i is going to be equal to 4 by -7 is what? -28. And I by I is what? I squared. Now, since I is equal to the square root of -1, I squared is going to be equal to what? -1. Right? So -28 times -1 is equal to 28. Now, division, 4i over -7i. The I is going to cancel out, leaving me with -4 over 7. Now I want you to notice that with addition, I ended up with an imaginary result, and the same thing with subtraction. But with multiplication, right, my result is now a real number. A number that no longer has that I in it. All right. Same thing with division. Just one thing to note there. Let's talk about powers of I now. I to the power of 1 is equal to I. Straightforward. And I just demonstrated up there that I squared will give me minus 1. Now what about I cubed? I cubed is the same as I squared times another I, right? So that's going to be what? The minus 1 times one more I, which will give me minus I. And I to the fourth is I to the third times another I. And what is I to the third? Minus I. Right? So I have minus I times one more I, right? Which is essentially minus I squared. And I squared we know is minus 1. Right? So I have minus 1. That's equal to 1. I to the fifth is going to be what? I to the fourth times another I. I to the fourth is 1, right? So I to the fifth is going to be 1 times I, which is I. And I to the sixth is going to be I to the fifth times another I, which will be I times I, which is I squared. And that we said that is equal to minus 1. I to the seventh is I to the sixth times another I, which is going to be minus 1 times I, which is equal to minus I. All right. Now, I want you to notice that there's a pattern here. Let me zoom out a bit. All right. So, I to the first power, I got I. I to the second power, I had negative 1. Then I moved to negative I. Then I moved to positive 1. All right. And then when I went over the power of 4, I had I again. Then I had minus 1. Then I had minus I. And if I found I to the power of 8, I'm going to have positive 1, right? It's a cycle. It seems to repeat itself every 4 powers. So at the bottom here, I kind of wrote this down so you can see and understand the pattern. Something a bit easy to remember. I'm going to explain it now. Let's say I have a random power n. Let's say I raise I to some power n, right? What you do is you take that power n and you divide it by 4. And whatever your remainder is going to help you to determine your result when you raise I to that power, right? So if I divide the power n by 4 and I end up with 0 remainder, for example, if that power was 20 and I divide it by 4, I'm going to end up with 5 and 0 remainder. And that's going to be this first case here, right? Then my result is going to be 1 when I raise I to that power. If I'm left with 1 remainder, when I raise I to that power, my result is going to be I. For example, if I raise I to the power of 21, right, my result is going to be I. If I raise I to the power of 22, right, because when I divide 22 by 4, I'm going to have 5 with 2 remainder. So I'm looking at this situation here. So my result is going to be minus 1. And when I divide the power by 4 and my remainder is 3, then my result is going to be minus 1. Minus I, sorry. So looking up here, I had I raised to the power of 23. When I divide 23 by 4, I get 5 and 3 remainder. My remainder is 3, so I'm looking at this scenario down there. So my result is going to be minus I. Same thing with I to the power of 99. If I divide 99 by 4, 99 divided by 4, I get 24 and 3 remainder, right? My remainder is 3, so I to the power of 99 is going to also be minus I. What about, let me guess something else. What about I to the power of 32? Well, 32 divided by 4 is 8. And I have 0 remainder, so I'm looking at this first situation up there. So I to the power of 32 is 1. Remove this. What about I raised to the power of 29? Well, 29 divided by 4 is 7 with 1 remainder, right? I'm looking at this scenario here. So I to the power of 29 is going to be I. All right, that's going to be it for powers of I. Let's move on to complex numbers. Now, a complex number is simply the sum of an imaginary number and a real number. Now, this complex number down here, let's say it's a generic complex number and it's written in rectangular form. A complex number written in rectangular form is represented as the sum or difference of a real number and an imaginary number. Right? So a complex number, again, a complex number in a rectangular form is essentially the sum or difference of a real number and an imaginary number. Now, the real part of this complex number, of course, is going to be this x, right? That x right there, and I denote this as real z, and that's going to be equal to x. And the imaginary part is this part right there, and the imaginary z is going to be the y. We don't include the I in this notation here. We're only considering the magnitude. Let's talk about the algebra of complex numbers. Again, the rules are still the same, like regular algebra. If I were to add z1 and z2, this will be minus 2 plus 5i plus z2 is going to be what? 3 minus 7i. I'm going to add my like terms. Minus 2 plus 3 is going to give me 1. And 5i minus 7i is going to give me minus 2i. Subtraction. Rules remain the same. Minus 2 plus 5i minus into 3 minus 7i. This will give me minus 2 plus 5i. That minus is going to distribute, so I have minus 3 plus 7i. Minus 2 minus 3 will give me minus 5. 5i plus 7i is going to give me 12i. Multiplication. Minus 2 plus 5i times 3 minus 7i. All right, multiply every term in the first bracket by every term in the second bracket. So I have minus 2 times 3, all right, plus minus 2 times minus 7i. All right, 5i times 3 plus 5i times minus 7i. All right, minus 2 times 3 is minus 6 plus minus 2 times minus 7i is going to give me positive 14i plus 7i times 3 is going to give me 15i, and 5i times minus 7i is going to give me what? Minus 35i squared, right? Minus 6, 14i plus 15i. Now I squared, we said that was what? Minus 1. So we have minus 35 times minus 1. So minus 35 times minus 1 is going to be positive 35. So I'll have minus 6 plus 29i plus 35. And 35 minus 6 is going to be what? 29. So I have 29 plus 29i. All right, division of complex numbers now. Z1 over Z2. Z1 was minus 2 plus 5i, and Z2 is 3 minus 7i. Now, the first thing we do is multiply the numerator and the denominator by the conjugate of the denominator. Now, the conjugate of a complex number is obtained by changing the sign of the imaginary part, right? It's written there. So, the conjugate of 3 minus 7i is going to be 3 plus 7i. So I multiply the numerator by 3 plus 7i, and I multiply the denominator by 3 plus 7i. I want you to really pay attention here. You're changing the sign of the imaginary part. So if by some reason the imaginary number was actually written as, the complex number was actually written as minus 7i plus 3, the conjugate of this complex number is not going to be minus 7i minus 3. No, it's going to be positive 7i plus 3. We change the sign of the imaginary part. The one with the I. All right. So I multiply. Minus 2i plus 5i, multiply everything in the first bracket by everything in the second bracket. So I have minus 2 by 3, minus 2 by 7i, five I by 3, 5i by 7i. All right. Yeah, imagine the line is straight. 3 by 3, 3 by 7i, minus 7i by 3, and minus 7i by 7i. All right. Minus 2 by 3 is what? Minus 6. Minus 2 by 7i is going to be minus 14i. Plus 5i by 3 is 15i. 5i by 7i is 35i squared. And we know I squared is negative 1. So it's going to be minus. That's going to be minus 35. All over. 3 3 is 9. 3 times 7i is 21i. All right. Minus 7i by 3 is minus 21i. And minus 7i by 7i is minus 49. Minus 49i squared. And we know I squared is minus 1. So minus 49 by minus 1 is positive 49. So I have plus 49. All right. Minus 6 minus 35 is going to give me minus 41. Minus 49 plus 59 is going to give me I, right? 9 plus 49 is going to give me 58. And 21i minus 21i is 0. So this is my result right here. If you want, you can express this as minus 41 over 58 plus 1 over 58i. All right? So the real part of the complex number z1 over z2 is going to be this here, minus 41 over 58. And the imaginary part, mz1 over z2, is going to be 1 over 58. All right? All right. Oh, and another thing. If I have an imaginary number z, let's say you're asked to find z asterisk, or z with a bar at the top here. This simply means that you're asked to find the conjugate of z, right? So if z is 2 plus 4i, then z asterisk is simply going to be 2 minus 4i.